Experiments have shown a region of water forms that appears to separate charge, creating measurable electrical potential, in some cases on the order of tens to hundreds of millivolts. In other words, water near a surface may begin to behave like a little battery. That is what we are going to explore today. But to get there, we need to walk through a few key ideas. We will look at some of the more unusual properties of water, how it behaves near surfaces, and why those behaviors might allow something like this to happen. Along the way, we will briefly ground ourselves in what a battery actually is. But don't worry, at its core, it is built on a very simple idea. We will begin with the broader concept of interfacial water, meaning water that behaves differently near a surface. And then we'll move into the work of Gerald Pollack, who describes a specific form of water called exclusion zone or EZ water. And once you see how those pieces come together, what sounds unusual at first begins to make a lot more sense. Now, water is usually treated as the passive background of chemistry, the liquid things dissolve in, the medium where biological reactions happen. But when scientists look closely at the physical behavior of water, they find that this molecule is far from simple. Water has a reputation in physics and chemistry for behaving in unusual ways. It has a remarkably high heat capacity, meaning it can absorb large amounts of heat before its temperature changes. It also has strong surface tension, allowing droplets to hold together. And unlike most substances, water expands when it freezes, which is why ice floats. These properties are not accidents. They all trace back to the structure of the molecule itself. A single water molecule is made up of two hydrogen atoms bonded to one oxygen atom. Sounds simple, right? Well, the geometry says otherwise. The two hydrogen atoms sit at an angle relative to the oxygen, forming a bent shape with a bond angle of about 104.5 degrees. That geometry turns out to be extremely important because it creates an uneven distribution of electrical charge across the molecule. Oxygen attracts the shared electrons more strongly than the hydrogen does. As a result, the region around the oxygen atom carries a slight negative charge, while the region around the hydrogen atoms carry a slight positive charge. Now, these are not full ionic charges, but they are strong enough to create polarity within the molecule. Water, therefore, behaves like a tiny electrical dipole. One side of the molecule is slightly negative, and the other is slightly positive. This polarity changes how water molecules interact with each other. Instead of moving independently through the liquid, they attract one another through a special type of interaction known as hydrogen bonding. In a hydrogen bond, the slightly positive hydrogen from one molecule is attracted to the slightly negative oxygen of a neighboring molecule. These attractions are weaker than true chemical bonds, but they are strong enough to organize how water molecules arrange themselves. Additionally, each molecule can form multiple hydrogen bonds at once, sometimes connecting with up to 4 neighboring water molecules. The result is a constantly shifting network of interactions linking water molecules together. But this network is not usually rigid. Hydrogen bonds form and break continuously, often lasting only trillionths of a second before rearranging again. Liquid water is therefore not a static structure, but a dynamic one. This leads to an important point that is often overlooked. Even ordinary liquid water is not completely random. Because of polarity and hydrogen bonding, water naturally forms temporary local organization. Water, in other words, already contains a kind of short-lived structure built into the way its molecules interact. And that natural tendency toward organization becomes especially important when water molecules approach a solid boundary. When this happens, their freedom of movement becomes constrained. They can no longer rotate and translate in every direction the way they can in open liquid. Instead, their orientation begins to be influenced by the properties of the surface itself. Essentially, the presence of a boundary begins to organize the behavior of nearby water molecules. As a result, hydrogen bonds begin to reorganize, and under those conditions, the temporary structure we see in bulk water can sometimes become more stable and more ordered. This region is often referred to as interfacial water. It is a thin layer of water that sits directly next to a surface, where molecular interactions between the water and the material begin to shape how the water behaves. And this turns out to be extremely common in the real world. In fact, most water in biological systems is not far from a surface. So, understanding how water behaves near surfaces is central to understanding water itself. And one of the key factors that determines what happens is the nature of the surface or interface that water encounters. Some surfaces are hydrophilic, which literally means water loving. These surfaces attract water molecules often because they contain charged or polar chemical groups that interact strongly with water's polarity. Common examples include many biological materials, gels, proteins, and certain polymers. When water meets these surfaces, it tends to spread out and adhere, forming close molecular interactions with the surface. Other surfaces are hydrophobic, meaning water repelling. These surfaces lack the polar or charged groups that interact strongly with water molecules. Oils and waxes are familiar examples. When water encounters these materials, it tends to bead up rather than spread out. The distinction between hydrophilic and hydrophobic surfaces matters because it changes how water molecules arrange themselves. Near hydrophilic surfaces, in particular, the polarity of water and its hydrogen bonding network can begin to reorganize the nearby molecules more strongly than in the bulk liquid. Instead of constantly rearranging in every direction, the molecules close to the surface can adopt more stable orientations and interactions. This leads to structured water. Structured water does not mean a different chemical substance. It is still considered water. The difference lies in how the molecules are arranged, especially near the surfaces or within confined environments. Water molecules can form arrangements that are more ordered than what we see in the bulk liquid, hence why they gave it the name structured water. Researchers have observed that the properties of water in these interfacial regions can differ from the properties of the surrounding liquid. In some experiments, the interfacial water layer appears to show changes in viscosity, density, or molecular organization. These effects can extend beyond just a single layer. In some cases, the region of structure behavior stretches outward from the surface for many, many layers. If water near surfaces can become more organized, the next question is how far can that organization go and whether it produces any measurable effects. One set of experiments that explored this question was carried out by bioengineer Gerald Pollack and colleagues. While studying water next to certain hydrophilic materials, they observed behaviors that were difficult to explain under ordinary expectations. The experiments often began in a simple way. Tiny suspended particles, sometimes microscopic beads known as microspheres, are dispersed throughout the water. These particles are small enough that they normally remain evenly distributed in the liquid, drifting through the fluid as it moves. But when a hydrophilic surface is introduced into the system, something unusual happens. Instead of remaining evenly distributed, the microspheres begin to move away from the surface. Pollack and his colleagues refer to this as exclusion zone or easy water. Experiments have shown again and again particles, dyes, and certain dissolved molecules being excluded from the water near a surface. One of the reasons this observation drew attention is the scale of the region involved. Normally, changes occur over distances of just a few molecular layers, but in these experiments, the exclusion zone appears to extend much, much farther from the surface. This raised an important question. What kind of molecular organization could produce a region of water with such distinct behavior? Pollack's interpretation is that the water molecules inside the exclusion zone reorganize into a more ordered arrangement than what exists in the surrounding liquid. In his proposed model, the molecules form repeating structures that resemble layered sheets or hexagonal patterns. These arrangements are sometimes described as honeycomb like, where oxygen and hydrogen atoms align in ways that create a stable network extending through the EZ region. Within this framework, the organized region has been suggested to have a molecular composition close to H3O2-. This means that the structured zone has a relative negative charge, while the positive charges or protons are displaced into the surrounding bulk water. It is important to note that the exact molecular structure of this region is still actively being investigated. That being said, Pollack makes an excellent case for it in his book, The Fourth Phase of Water, and I highly recommend you read it. Alongside the structural interpretations, another surprising observation emerged from these experiments. Measurements showed that the exclusion zone carries a negative electrical charge, while at the same time the water just outside the zone appeared to be relatively positive. In other words, a separation of charge occurs between the EZ region and the surrounding bulk water. One way this has been interpreted is through the displacement of protons. As water molecules reorganize near the surface, some hydrogen atoms leave the structured region in the form of positive charge, creating hydronium ions in the bulk liquid just outside the exclusion zone. If the exclusion zone retains a relative negative charge while the surrounding bulk water is enriched in positive charge, the system begins to resemble something familiar in physics: charge separation. At its most basic level, a battery is not defined by metals, wires, or complicated chemistry. A battery begins with something much simpler: two regions that carry different electrical charges. One region is relatively negative, another is relatively positive. That difference in charge creates what physicists call an electrical potential difference or voltage. If those two regions are connected by a pathway that allows charges to move, the system can produce electrical current. And that is the principle behind every battery, from the small ones in electronic devices to the large systems used for storing energy on electrical grids. So, when researchers studying exclusion zone water observed this charge separation, it naturally raised an intriguing question. Were they looking at a microscopic battery? In several experiments, researchers have measured this electrical potential using tiny electrodes placed near the surface and in the surrounding water. Some experiments have reported voltage differences on the order of tens to hundreds of millivolts. Those values are small compared with many engineered batteries, but they are large enough to indicate that electrical energy may be stored in the system. Another observation adds an additional layer to the story. In experiments conducted by Pollack's group, the size of the exclusion zone appears to increase when the water is exposed to light, particularly infrared radiation. Infrared light is abundant in the natural environment. It is a major source of sunlight, and it also is emitted by warm objects in the form of thermal radiation, which humans emit plenty of. When infrared energy is introduced in these experiments, the structured region next to the surface sometimes expands significantly. This does not mean that infrared light is breaking apart water molecules. The energy of infrared radiation is far too low to break the strong bonds between hydrogen and oxygen. Instead, the proposal is that infrared energy may help drive the molecular reorganization of water, providing the energy required for the formation or expansion of the ordered EZ zone. In that sense, the system begins to resemble something like a charge separation device powered by electromagnetic energy, which is why some researchers, including Pollack, describe the phenomenon as an interfacial water battery. Not a battery built from metal plates and chemical reactions, but a system where the structure of water itself helps create separated charge. And perhaps the most important open question at this time concerns its biological relevance. Because if structured water stores separated charge, what is this electrical potential doing in the body? I mean, in our bodies, water is constantly interacting with proteins, membranes, DNA, and surfaces. Even cells are full of hydrophilic interfaces. Every membrane, organelle, and polymer structure represents a potential environment where water molecules are constrained and organized. If charge separation emerges naturally in these conditions, then water would not simply be the background medium of biology. It could also participate in the flow and storage of energy within living systems. Even if the details of the exclusion zone model continue to evolve, the broader lesson is already clear that its polarity, hydrogen bonding, and sensitivity to surfaces allow it to reorganize in ways that, under certain conditions, produce separated charge. Which brings us back to the surprising statement that started this video. Water near a surface begins to behave like a tiny battery. Based on Pollack's extensive experimentation presented in his book, I wholly agree with that statement. What it all means, I am still trying to make sense of. On that note, I sure hope you let me know what you think. I so appreciate you making it to the end. And if you enjoy science at the edge and beyond, I hope you'll consider becoming a member of this community. Please subscribe and like this video. Until next time, stay curious and take care.